recording, now recording. Do you see my whiteboard? Do you see? Okay, the big questions I want to try to explain now is we have in the multiple integral, we have substitution. Oh, no. We have substitution. And we have parametrization, no? Basically, we study parametrization. Okay, for example, substitution you apply in double integral or in triple integral. So, no, it's completely out the vector calculus. Okay, you do substitution, the most popular substitution is polar in double and cylindrical and spherical en triple. Ajá, pero en vector cálculo, entonces we start new zone, que es parametrization. Que parametrization we are using to compute la integral. It doesn't matter que es vector field o no, or scalar, doesn't matter, pero you parametrization the curve or the surface integral. You parametrization the surface, remember the parametrization the surface contain two parameters because it's two-dimensional object, and the line integral no, it's one dimension, so we have only one parameter. Okay, so my idea is, what do you think? Any opinion? This is the same thing with different thing. Porque sometimes happen, look, por ejemplo, Lola es Lola, pero es Lourdes. Pero it's the same person, no? Two names for the one person. Entonces, maybe that sounds similar, at least in my intuition, no? What do you think about it? It's the same, it's different. It's the thing I try, but I need opinion. I need to explore your intuition. Okay, your intuition is good because you are advanced students. Opinion, guy. Activate the microphone. A ver, one by one. Álvaro, I need the opinion. Álvaro, Sean, Finol, Alejandro, Lion Hall, Lola, of course, Daniel, and Josué. Opinion. So you have no opinion, say no opinion, but say something. No opinion, it's the same, it's different. In my opinion, my intuition say this is two different things, or is the thing with different name. What do you think? And little by little, my intention today is clarify this idea. Why I try to clarify this. This is completely weird. No book touch this. No book commit me in this area because it's complicated, right? However, the mathematician try to discover, the partners of the different particular case to make a big conclusion. This is like an induction. So like a detective of FBI. And this is double integral behave like that, triple integral behave like that, line integral behave like that, double integral behave like that, or surface integral, behave like that. So you integration this idea together and you discover si es the same or it's different, or maybe it's a historical fact que es different name. I don't know. Opinion, no opinion, guy. Álvaro, tell me something. You say no opinion. Oh, yes, it's the same or it's different. Álvaro. Sean. Guy. I try to ask for your participation. You're there or you're sleeping? Lola, are you sleeping? Alejandro, what do you think, Alejandro?
No opinion.
No opinion. Okay, okay, no problem. But do you understand the problem, right, Alejandro?
Yeah.
Álvaro, come on, quickly, you know, we spend the time on that. Come on, you are not kindergarten guy. Josue, what do you think? Is different thing, is same thing, or is no? I don't know. Lola, Eduardo, Sean, Álvaro, come on, guys. Ah. No, but I try. At least I need to hear opinion, no? Or no opinion. Okay. Well, entonces, let me try. For example, do you see whiteboard again? Okay, for example, double integral. Double integral. Double integral. Double integral. We're doing example. Let's take one arbitrary example, okay? We did before. And we should have this integral, for example, integral from -3 to +3. This is completely arbitrary example. From 0 to square root 9 minus x squared of sine x squared plus y squared dx dy. Entonces I focus no en the integral function. This is not important. Well, no, it's important, but not extremely important now. And we focus in the region que generate this double integral. Entonces this region is obviously a circle, no? A circle because the equation of the y equal. So, but wait a second. This is dy. Yeah, I make a mistake here. This is dy dx. Dy dx. The equation for this circle obviously is x squared plus y squared equal 9, no? But when you solve y, you get that part. And basically from 0 to this is because this integration we are doing this direction. It's only semicircle. Yes, from 3 to -3 when you extend the window. So basically, this is my region. Okay, call R. As always. However, we are doing change of variable to polar maybe. So you convert this integral to another integral. Of course, this is sine r squared. Remember, you need to replace it. Any variable in Cartesian x and y by polar, no? Entonces, the polar we have r and theta. Okay, we have the Jacobian, que es the r dr and polar d theta. Entonces now r vary from 0 to 3 and theta vary from 0 to pi. Now we're solving this because this is easier than this. And the reason it's easier than this is because one interpretation is, suppose that we have a new plane, que es the plane theta r. I know it's not like that, but in my mathematical imagination, the thing I did basically was a change of variable. You change the traditional coordinate xy, and the new one is r theta. And so we have como the limit is constant. Wow, cool. This is 0 to pi. This is 0 to 3. Entonces you see que the new region is a rectangular. That is the reason it's easy, the solution of this. This sounds familiar a little bit with the parametrization, I suppose, but no, but when I do the parametrization, professor, I never talking about Jacobian. In this case, we need the Jacobian. And remember, the Jacobian, in this case, is a determinant. Let me see the representation, the notation for the Jacobian, is something like that. Del x comma y, delta, u comma b. Yeah, actually, in this example, it's no u comma b, it's r comma theta. But now it's okay because I want to explain in general, no? Entonces es determinant, in this case, 2 by 2. It's 2 by 2. Let me explain why it's 2 by 2. When it's 2 by 2, and the element here, the 4 element, let me use in this notation, it's partial derivative x with respect to u. Get this part. Partial derivative x with respect to b. Partial derivative y with respect to u. And partial derivative y with respect to b. This is equivalent in all the notation, partial derivative x with respect to x, right? But this is with respect to u. Sorry, u. This is too long notation. This is more clear because we are studying now everything. So the convention is doing this way. Now remember, in the organization for the Jacobian, we can put x, y, y, or you put x, y, y. So you transpose the row and the column in the one determinant, the answer is the same. It's not important. Okay. Entonces, one important idea que I omit when I explain this is that when you compute the Jacobian, you need to find the absolute value of this. Let me copy ABS. I don't put the traditional notation, the absolute value, like that, because those says absolute value determined, those says double bar, those says confusing. I put ABS. ABS is absolute value. So when you compare this determinant, suppose que es numérica. Sometimes not numérica, sometimes it's a function. Pero suppose que es numérica, and the answer is 20. Okay, it's 20. Pero si es negative 20, entonces the Jacobian is positive 20. And the explanation or the reason que it's absolute value in the lecture que I explained was because this Jacobian represents the scale factor. Que es, see the area in this case is, I don't know, it's 20. If the area here is 10, the scale factor is 2. Entonces the Jacobian is equal to 2. And si es geometrically interpretation, there are no sense to talk about negative quantity. That is the reason that you take the absolute value. So mathematically, yeah, is your organization the determinant, the computer determinant, and find the absolute value because it's a scalar factor. And everyone has said this. Professor, I agree. I want to prove what's the reason behind this absolute value, mathematically speaking. But this is in the last moment of the class today. Okay, everyone follow me? Entonces, one more thing. What is the reason that the Jacobian is 2D? So 2 by 2. Because the transformation that we are doing in the region R and the region S, I want to call this region, is 2 dimension. So that's the reason that the Jacobian is 2 by 2. So far it's clear. Everyone follow me? So the new two new details. I never write this region when I explain intentionally. I never explain clear absolute value. Where come from this? Well, I explain, but using the idea for the scale factor. Okay, and this is the key to understand the difference between parametrization and substitution and multiple integral. Suppose triple integral. Suppose triple. L integral. Okay, and triple integral. Let's come back to the example to make more understandable. The example, one example we are doing before is the example -1 to 1 negative radical 1 minus x squared 1 minus x squared and x squared plus y squared, this is square root 2 minus x squared minus y squared, and the integrand part is dz dy dx divided by something, divided by z square root. This is one example we did before. I saw you look in the surface que participate in this integral. This is a sphere, or at least hemisphere. And it's a cone. Okay, so the three-dimension picture in Cartesian of this solid que represent the region of this triple integral. Bueno, it's a hemisphere. By the way, the radius is radical 2. As you don't understand something, let me know, guys. Radical 2, hemisphere. And the cone. I suppose you remember this problem. Because it's in between the sphere and the cone. Okay, so this is our region. Okay, obviously, this region is 3D, 3D. This region normally we call T, que es 3D. Okay, entonces, using the magic of the substitution, we can make a decision to change to a spherical coordinate. We manipulate the integrand part, put the Jacobian. Remember, the Jacobian is the Jacobian in spherical is rho squared sine phi d rho d phi d theta. And use substitution C by rho cosine, whatever, blah, 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 blah. You have inside the integral function tangent phi d rho d phi d theta. And the limits go from 0 to radical 2 and rho, que is that part, from 0 to pi over 4 and phi, pi over 4, not 2, pi over 4, que is from 0, que is on the z-axis to the outermost side of the solid, and from 0 to pi, because it's full around. Okay, so now using this, we convert our region T, or our solid, que es region, no? So a region in 3D is solid T, and our another region also in 3D, but the limit is a constant. And the ordering is, for example, I take here, doesn't matter the order, rho, theta, and phi. Así, entonces, si the limit is a constant, es obvio que our new region, que what I want to call D, que es 3D again, look like a box. What box? Bueno, en rho es radical 2. En theta es 2 pi. It's bigger. And en phi es pi over 4. So it's a box like that. It's a box. Entonces easier compute that because you take advantage que the limit is a constant and you separate in three single integral like Cal1 and that's it. So in this case, the transformation is 3D, 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 3D. Therefore, the Jacobian that you expect is a determinant 3 by 3. Okay, I understand very well. The Jacobian notation is Jacobian. The variable in Cartesian is x, y, z. And the variable in spherical, for example, in general, UBW, suppose hypothetically a substitution. This was example, but in general, I call generically UBW in our specific example, for example, U is rho, B is phi, and W is theta, no? But it's okay. It's just a name. Entonces, X, 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 Y, 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 the organization of the Jacobians, Z, 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 and you differentiate with respect to UBW, UBW. Basically, this notation means partial derivative x with respect to u, no? Partial derivative x with respect to b, partial derivative x with respect to w. And don't forget the famous actual value. Because, again, the representation of the geometric interpretation for this Jacobian is a scale factor. A scale factor between this volume of the region D volume, okay, highlighting this color, and the volume of T, okay, not necessarily is the same, but we have a scale factor, and this is the representation of this. So far, everyone follow me, no? Because you know very well this, somehow. I introduced a new idea, no? But basically the same, the majority of the concept is very well known for you. Let me try now to go to the world of the vector calculus in which you study line integral and surface integral. Let me start line integral first. Of course, we are talking about line integral, no in vector fields, in scalar function, to simplify the thing and to compare. Entonces we are using same condition. Entonces in this case, we have two possibilities, no? We have the possibility that we have in two dimensions, xy, a line, a curve, no line, and you parametrization, and to parametrization using t, so x equal xt, I call it generic like that. And t is a parameter that varies from a to b. Therefore, thanks this transformation, my interpretation is a line is a t, line axis, this is a and b. And this is my interval. So basically, any point in between the curve somehow is represented in one line. Therefore, the transformation is 2D and 1D. It's the first thing that happens, that there are no coincidence in between the dimension of the region, the original, and the after the parameterization. I suppose that this is the small differences between changing variable and parameterization. Okay. But no Jacobian, never I talk about Jacobian here. Parameterization, you're doing solving, end the story. Entonces, how we compute the line integral? Well, the line integral of the scalar function ds. Remember, ds is no surface, it's r length. Entonces, no, to differentiate that, I put s, pero no capital. Es your integration to convert this integral in the single integral of calculus 1 from a to b. You replace x for the corresponding parameterization, que es this formula, yt. And you put here the r length formula. Que the r length formula is derivative x with respect to t square. Let me put a square here. Plus derivative y with respect to t square. Dt. And where come from this? Well, I come from the Cal 2. Okay, you know how we compute the r length. It's a formula that we study exactly the same. Maybe the professor in Cal 2 explained a little bit different. Right, like that, square root dx dt square plus dy dt square. Dt outside is equal to this. And see your integration, and between two values, a and b, you obtain the r length of the curve. Okay. So never we're talking about Jacobian, because Jacobian is determinant. And determinant normally is 2 by 2, 3 by 3, but Jacobian 2 by 1 from this different dimension. I never see before in my life this. But let me try to understand. So you have applied the notation for the Jacobian, okay, is this. But you have t, because we only have one variable. So basically, it's Jacobian of the one region in 2D and one region in 1D. So I suppose que es using the same corner. It's the determinant 2 by 1, but I never see before rectangular matrix determinant. You put in the majority of the software professional and say it mismatch in dimension. Okay. So this is partial derivative x with respect to t. Look, partial derivative x with respect to t, and this is partial derivative y with respect to t. Entonces now, using the, the analogous idea, you see that this should be, I don't know, question mark, it's true, that part. Square root x prime square, as a function of t, no? So you differentiate square plus y prime square. Then the formulas to compute the determinant when there is no square and rectangular is different. Okay. Let me try the same line integral, but now, suppose now, okay, we have a space in 3 dimensions. We have a line in 3D, and we are doing the parameterization of this line in between one specific interval, x equal x of t, y is equal y of t, c is equal c of t. And t vary from a to b. It's the same, but including the third variable, can see. And likewise, when you are doing the, this is the representation, it's the same idea, a to b. This is the domain of the t parameter, no problem, I understand. Okay, and this convert point by point, any point on the curve to any point on this. So it's the conversion now 3D, 1D. Wow. More difference in the dimension. And I study with the professor explained that bueno, wait a second, we have three variables, the integral function is analogous to this. It's integral from A to B, so we change the classical variable x, y, and z for only one, que es t. And you replace in the formula x as a function of t, y as a function of t, z as a function of t. Okay, and the part of ds is again square root of the derivative of the parameterization one by one. So you differentiate x prime s squared plus y prime s squared plus c prime s squared. And don't forget dt. Dt is the differential of this single integral, exactly like a Galois. And one more time, see, I try to do I never see that Jacobian in line integral. No, the professor no book explain this because we have a contradiction. We need determinant que is no square, a rectangle. Wow. So now the Jacobian in this case is we have three variables x, y, z. Suppose this is my supposition, my secret piece of paper. With respect to t, que es only one parameter. Y I suppose que that part is square root x prime square. When you talk about prime, it's partial derivative with respect to t, que es the only parameter. So you want to write like that one because it's ordinary, right? Entonces, y prime square plus c prime square. Okay, entonces one more time, look like, entonces this, let me try, the determinant in this case is partial derivative x with respect to t, partial derivative y with respect to t, partial derivative c with respect to t. This determinant is, of course, rectangular, 3 by 1. Entonces, look like I discovered the solution of the determinant que es no square, que es rectangle. Wow. Is like a square root of the sum of the square partial derivative separately, put together inside the square root, and you compute the value of the determinant and matching perfectly with the idea. But on the moment I explain this, I never using the word Jacobian, I using Marlene. But you know, this is the beauty of the mathematics. You travel for the one path. You travel for different paths. You get to the same point. It's because it's the same. It's a coincidence. But okay. Not enough. Not enough for me. I try to investigate now surface integral. And let's see what happens in the surface integral. We study surface integral. Of course, again, we're talking about using a scalar function. No Victoria. To make fair in the comparisons. Now we study in 3D. We have surface. Of course, this surface, like a region, is 2D. Lo que living in the ambiental 3D. Okay, X, Y, Z. And you somehow decompose in 2D. So in one domain 2D, que suppose it's like that. It's a suppose the frame of UV, que maybe is spherical or no, or general UV. And the formula is, the parameterization is x equal x ub, two parameters. So that any component in x, y, and z is represented by one function que generica I call x, y, z, the same name. But no, actually, I can call f, g, h, whatever. ub, and c is c, ub. And b vary. For example, u vary from a to b, and b vary to c to d. Are you familiar with this idea? This is a, this is b, this is c, and this is d. And this is my new transformation. This is I call, for example, and this guy is S, and this I call S prime, maybe. I don't know. Entonces, the idea behind this is, well, okay, you have the surface integral in one scalar function. And this is ds, and this is the surface, no r length. Entonces, using the parameterization, we transform this like a double integral in the region S prime, like this. It's easy because it's rectangular. But the only thing you should do is substitution. X for the corresponding function is x u comma b, y u comma b, comma c u comma b. One by one component replaced by u and b. And the famous ds I explained in your moment, que es the magnitude or actual value RU, so the cross product, du dv. Okay? Entonces now, following the same idea que we almost discovered, this look like a Jacobian. Maybe, I don't know. But in this case, we are doing the transformation, the 3D and 2D. Therefore, the Jacobian and the original variable is x, y, and z. But in the new variable, the parameterization is u and b. Therefore, you expect one determinant that is 3 by 2. 3 represent the dimension of the original space, 2 represent the dimension of the new space. So all we have, and you put x here, y here, z here, and you differentiate with respect to u and b, u and b, u and b. Okay, so now according to this, the problem is, Professor, how you solving determinant rectangular 3 by 2? No, I don't have idea, but following the same pattern that we learn in our length, we put the big square root, and you take the collection of the element inside this, square each other. Let's see what happens. I don't know. So say you take, for example, one determinant 2 by 2. Okay, it's xu, xb, u, yu, and yb, no? You take another combination, is xu again, xb, cu, cb, squared, and we have 3 combinations, no? 3 by 2 is combination 3 by 2 is 3, no 6. Entonces, the last one is, suppose the last one, that part is, wow, yu, yb, cu, cb squared. Okay, this is the idea, using the imagination and the other formula that we see in one dimension. Wow, Professor, but I never see this equation in the surface integral. Of course, you never see that. However, let me try to adaptate this equation in one particular example that you very well know. Suppose that I taking explicit form. Remember that there are three different ways to solving surface integral. The classical parameterization that I try to do here, the explicit and the implicit. The explicit is the most popular. It's not the best, no, depending on the example, but it's good to understand. And explicit, the idea is clear. X is X, no U, no. Y is Y, no B. And C is f of x comma y. This is the idea for it, for the explicit. Then, if you try to do your best in this formula, let's see what happens. This is partial derivative x, but u and b do not exist now. Exist the two parameters is x and y only. So this is suppose que u is x and suppose que b is y. So this is partial derivative x with respect to x, and this is partial derivative x with respect to y, and this is partial derivative y with respect to x, and this is partial derivative y with respect to y. Cool. And this is partial derivative x with respect to x. Remember, in your mind, I change this like a u, and this is b, right? This is partial derivative x with respect to y, and this is partial derivative z with respect to the x, and it's a partial derivative z with respect to y. And the last part is y with respect to x, y with respect to y, c with respect to x, and c with respect to y. Okay. Okay, it's doing. Partial derivative x with respect to x es obvio que es 1. This is 1. You differentiate this with respect to x is 1. You differentiate x with respect to y is 0. You differentiate y with respect to is 0. And you differentiate y with respect to 1 is 1. Oh, it's easy. This is the identity matrix, and determinant of this is 1 and 1 squared 1. But okay, no problem. Let me try it, continue. Okay. Partial derivative x with respect to x, again is 1, I did that. This is 0. Be careful this. This is the c, and c is cx is derivative f with respect to x. Let me use in this notation. This is f of x, and this is f of y. And this part is partial derivative y with respect to x is 0, partial derivative y with respect to y is 1, and this again is fx and fy. Okay, almost we finished, guys. Okay, you compute this determinant. It's so big as 1. 1 plus something. Compute this determinant, multiplication like that. It's so big as f of y squared. This is 0. And here is f of x squared. And this is dx dy, and you are super familiar with this formula. Wow. Was everything matching? Everything matching. Nobody, no book talking about Jacobian. And Jacobian is exactly the same for substitution. Or no substitution, sino es ds, es the formula. But I have more. The last moment. Remember, when you have Jacobian in 2D or in 3D, so when you have Jacobian 2 by 2 or 3 by 3, we never apply professor square root. Well, the reason is, okay, for example, in 3 by 2, we have three combination of the 2 by 2 determinant. This combination, or the last combination is the first row and the third row. But in this case, no. In this case, we have completed the collection. X, X, Y, Y, U, B, U, B. So we have only one combination. Likewise here, X, 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 Y, 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 C, C, C. And we have here U, B, W, U, B, W, U, B, W. So we have only one combination 3 by 3. No, this is not symmetric. So because it's rectangular. So now you can apply the formula of this. Of course you can. So suppose I compute this is a square root, but we have only one combination. So you copy this determinant again here and you square. This determinant I copy here. Bam, 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 bam. Copy paste. And you square. Plus no more combination because it's perfect square. And it's a rectangle. We have three combinations. Oh, another combination. And you see, wow, look at that. So you square something and you find the square root, you are doing nothing, right? Well, you are doing something. You are doing absolute value. Yes or no? Absolute value of this determinant. This is the reason to explain and integrate everything. Absolute value. Wow, look like fantastic. Yes or no? What do you think? Any opinion now, guys? Any opinion? Say something. Don't say, wow, I don't understand anything, or okay, this is the like motivation. No? Some people get like the mathematical try to continue apport new idea behind this problem of the parametrization of the to explain this in the efficiency way. No? Opinion, no opinion. You are completely mute. No? For the new student, I send in this email the final test. Don't hesitate to take if you want to improve your grade. You compute by yourself. You adding test 1, 2, 3, 4 online and reading. Divide by 8, compute the average. Entonces now, if you get 80 something, it's B. No? You got 90 something, it's A. 70 something is C, 60 something is D, or below. Entonces, you want to improve, you predict improve, take. The final is super easy. You see que es ridiculous easy. I grade that y I include in the equation in my secret formula. And always improve. Suppose you don't know anything, no problem, 0, pero no doesn't affect in the formula. Always affect in positive direction, never affect in negative direction. Cool. So, opinion. So what is your conclusion? Parametrization and substitution is the same or no? And the mathematician explain in different way. I don't know why. I am confusing. Or I am more clear a little bit. No? Open the door to research something here. Okay. Okay. No opinion. Guys, I frustrate. I say opinion, you don't say something. Come on. The advanced student. Davey, Max, Theo. Theo, you are in Miami or in Argentina? David, you say something. Come on, activate the microphone.
Oh no, I was just looking at the final while you were saying that.
Okay, yeah, Argentina. Okay. The final I sent today, and do you want to resend? I want to resend again in the video of this. Okay. You take and the same today. Remember, Okay, I need to turn in to the department the final grade in the morning of the July 29th. So no delay. No delay. After that it's late, entonces I don't know, including the formula. And you know how complicated is change one grade after I submitted. It's very complicated. I need to make a lot of paper and explain clear why is the mistake. So please don't do that. Okay? And the rest of the time we have, I want to explain another thing. Another thing is, okay, I try to ask myself is about, we study different theorem. We study, for example, fundamental theorem of calculus in Cal 1. We study Green Theorema, fundamental theorem of calculus in line integral, and so on. So now I want to discover again a partner que condensing everything. Okay, maybe it's the same or no, I don't know. But this theorem somehow involved one region and its boundary. For example, let me try to explain this. Okay, look, this is the whiteboard. Do you see whiteboard?
Yes, we see it.
Okay, cool.
By the way, Professor, you said the final's optional, right?
Sí, optional. Suppose que you compute the average. It's David, no? It's David?
Yes.
Suppose you compute the average. You get 85, is B. B is good for you. So don't do anything. You grade B. It's to improve. So you need to improve. Okay? So now, let me explain. So basically, any theorem somehow talking about integral, derivative, antiderivative, double integral, line integral, triple integral, and different derivative like in multidimensional gradient, curve, divergence. Okay? And the most important to understand is we have a different region, maybe in 3D and 2D. Suppose, let me try to explain the easy, in my opinion, is in 2D. Suppose we have surface. This is surface. Surface 2D. 2D object, because it's not solid, no? And the boundary is this curve C. Normally in the book call it delta S. That's a notation they use in the book. This is the boundary. So we have any theorem somehow involve region and boundary, region and boundary, region and boundary. And one direction is derivative or something similar to the derivative like a gradient, curve, divergence. Que es operator que somehow involve derivation, partial derivative or ordinary derivative. And in the opposite direction, well, okay, is the Divergent Diorama or Stuck Diorama or whatever. Okay. So now I try to condensing these two information in one picture because I want to discover see we have a partner or no. I put in red color the different three possibilities we have, que es 3D. Look, and there is ambient 3D, ambient 2D, XY, or ambient 1D, que is only the x-axis. Cool. Let me start for the ambient 3D, que is the most interesting, no? We start at the beginning with the scalar function. Okay, cool. W is equal f x comma y comma z. And we can compute the gradient. This is the notation for the gradient. And automatically the result that you obtain is a vector field because the gradient is a vector. I call G. You know the formula for the gradient. Cool. Now after that, I compute the curve. I want to compute the curve on this vector field. And you get another vector field. And this is the formula for the curve. And finally, we compute divergence, que is another operator, on the vector field, but you obtain a scalar function. And stop. Why stop? Because you start the story from the scalar function and you ending in the scalar function. Cool? Now, in the opposite direction, you don't differentiate, you integration. Let's do it here. For example, Divergent Diorama is a theorem que state connection in between surface integral. By the way, a closed surface is this, and triple integral and the solid. In this case, the region is 3D because it's solid. So the region D, in this formula, they call different name, and the name I call in class. No? The solid D and the surface S. The region is 3D, however, the boundary is 2D because the surface. We continue backward. In the opposite direction, we have another theorem like this. This is 2. Okay, state the connection, look at the formula here, look at the figure here, and between one region is 2D, the surface, and the boundary is 1D, because it's a line. So the line of the curve, the closed curve. In the opposite direction, finally, to come back at the beginning, we have the famous fundamental theorem of calculus and line integral. Fundamental theorem of calculus of line integral, in which state the connection between one line integral and the potential function. In this case, they call f. Normally, I call phi. It doesn't matter. Okay, entonces, in this case, important to understand that the region is 1D because it's a curve, the dimension for the curve is 1D. However, the boundary, the endpoint, is 0D because it's the point. Do you see that? Beauty or no? Tell something, guy. Yes, I got it.
Yeah, we see it.
Now, suppose que I decreasing the dimension of the our problem. Okay, now my ambiental is no 3D, it's 2D. Okay, no problem. We start again with the scalar function que contain two variables, x and y only. Okay, no problem. I compute the gradient, and the gradient is a vector field, obviously. Vector field in 2 dimensions. And we compute the curve, and the curve, remember the curve in 2 dimensions is non-vectorial, it's a scalar. And we come back again to the scalar function and stop here. So when you decrease in the dimension, I can see okay, we have similar, but it's shorter. It's short. So when I go back, okay, the opposite direction, no differentiation, no integration, and this part is the green theorem. It's very, very analogous. Look, look. It's no coincidence. This is the beauty of this. This and this is the same. This and this is the same. And here, no. It's not here. No. We lost that part. And so now, the green theorem is say where the connection between double integral of the curve is exactly the same, this expression, and the line integral and the vector field fg is something. The region is 2D because it's flat, but the boundary is 1D, que es el curve. Okay, so now, in the last line is the fundamental theorem of calculus of the line integral, but in 2D, not in 3D. The curve is 1D and the boundary is 0D. Exactly coincident this idea, guy, and this idea. Okay. And finally, when you restrict it in 1D, well, you have only one step. And one step is, suppose we start with the scalar function, cal1, only one variable, single variable. And now we have no gradient, we have just derivative. So in cal1, the teacher talking about derivative, never talking about gradient, because gradient is the derivative component by component. And you get the scalar function, and in the story, you have two steps to block. And in opposite direction, you have the famous fundamental theorem of calculus that we studied in cal1, in which you have region 1D, pero horizontal, ¿no? Oblique, maybe si es integration with respect to x or integration with respect to y, pero never we integrate in one curve intermediate, one line intermediate. So it's x or it's y in cal1. Entonces the region is 1D and the boundary is 0D because of the endpoint. Wow, fantastic. Do you see that? Suppose we have, I open the door to the another calculus working in 4 dimensions. Wow, entonces, I suppose, this is crazy. The reason it's crazy is because I have no sense to talk about 4 dimensions because there are no physical meaning. But suppose you have one block here, 4 dimensions. So we have complicated thing. We have more law on this, right? We have another operator, maybe repeated gradient curve, divergent, but we have another, and we have another theorem when you go back. But basically the application in physics and engineer is in 3D. Cool? Do you like that? Yeah, it's interesting. No, you know, it's topic interesting, and that's it. Now, we finish, guys. Let me say something. 2 things important. Are you clear everything? Are you clear everything to finish the semester? Are you clear, right? Yes? Yes. Okay, cool. Number 2, if you like my lectures, and you get good grade, of course, I appreciate so much that you express your opinion and ratemyprofessor.com, because this allows to another students take with me this class, maybe in the next summer, right? Okay, because I appreciate so much, and this is totally anonymous. Okay, you express your opinion, free country. Okay? Okay?
Okay.
You promise. David, you promise. Hey, Max? Theo? Finol?
Yes, Professor.
Good. Ernest, you have some pending tests, right? Checking the Blackboard guy. Any problem? Mira, Lola. Okay, so if you don't finish, you know what is the result. Lola claimed me. Okay, pero the problem of the Lola was the name. Lola is not Lola. Lola is Lourdes. Entonces now I confusing, pero I fix it. This is no big deal. Okay, guys. I am happy to teach with you. Next, see in another class can you take with me, maybe differential equation, something. Okay, Profe. Okay, bye. Bye, guys.